All right, in this little talk, we're going to look back at things that we've already learned and pull them together as an introduction to exploring something called the ionization energy of atoms. So our learning targets, number one, recognize that since atoms interact by means of their electrons, the arrangement and behavior of electrons determines the properties of an element. So our main focus is to find out how the electrons are arranged and how they behave. Now, number three, we're going to relate the electron arrangement to the structure of the periodic table. You saw that the periodic table is arranged according to the properties of the elements, both the physical and chemical properties. And since those properties are determined by electron arrangements, there is a connection. And then finally, we are going to analyze the data or electron ionization energy data in order to understand how electrons are arranged in atoms. So this is to pull together things that we know from the past and prepare you to analyze some data and learn for yourself how electrons are arranged. So recall, here is a representation of an atom using something called an electron cloud model or orbital model that we'll learn more about. That's the nucleus in the center, and the kind of hazy dotty things are the area in space, the region in space where the electrons are. All right, so recall, atoms have a positive charge that is fixed. We now know that that is in the center, and we call it the nucleus. And they have electrons. The electrons can come and go. Okay, electrons all have a negative charge. Opposite charges attract. So the electrons are attracted to the positive nucleus. The nucleus is also, of course, attracted to the electrons. Like charges repel. So electrons repel other electrons. That's not going to be super important today, but we are going to do more with it later. Also recall, way back to the beginning of the course, energy is needed to melt solids and vaporize liquids. We said something attracts the particles together in the solids and liquids. And when things are attracted together, it takes energy to pull them apart. So that potential energy of phase change or phase energy is the energy that is needed to change the arrangement, that energy that is needed to pull things apart. It takes energy to pull things apart when they're attracted together. All right, since electrons and nuclei have opposite charges, they are attracted to one another, and energy is needed to separate them. This little diagram shows a representation of a hydrogen atom on the left with a nucleus with a charge of +1, an electron -1, and a helium atom on the right with a nucleus with a charge of +2 and showing the attractions to one of the electrons. The electrons, which are negative, are attracted to the positive nuclei, and these energies listed down at the bottom, kilojoules per mole, that's an amount of energy, tells you how much energy it takes, this is per mole, to remove one electron from the atom. It takes more with helium, might have something to do with that larger charge in the nucleus. Usually we talk about removing an electron from an atom. Since the electron has very tiny mass, it is much easier to move. So because nuclei and electrons have opposite charge and are attracted together, energy is required to remove an electron from an atom. Because an atom that is short of electrons is an ion, the energy needed to remove an electron is called the ionization energy. Now remember, in chemistry, we can't tell what is going on just by looking. We do experiments to see what matter does in order to figure out what is going on. We will look at data on ionization energies of different elements to try to understand how their electrons are arranged. Here's a table showing some ionization energies, elements listed in the first column, sodium, magnesium, aluminum, silicon, etc., and then the energy to remove one electron, and then a second electron from the same atom, and a third electron, and a fourth, etc. So this is a table of ionization energies. This is the type of data we are going to be looking at. So let's make some predictions. We know the attraction of opposite charges is greater when the magnitude of the charge is greater. and when charged objects are closer together. So the bigger the charges, the stronger the attraction. The closer together they are, the stronger the attraction. So prediction 1, how will the ionization change from element to element as atomic number increases? So the charge of an electron is the same, but we're talking about a nucleus with a bigger and bigger charge. How will the attraction change? If the attraction gets stronger, we expect the ionization energy to become more. Prediction 2, if we remove more than one electron from the same atom, how do you think the energy needed will change from one electron to the next? And we're going to jump over and look at the atom builder for a clue on this. I've got an atom already built. Here's the way we looked at it. Nucleus in the middle, electrons around, but there's also this electron cloud model that we're going to talk more about. And this is useful for visualizing this. Watch what happens as I remove electrons. There's 1. There's 2. There's another one. So what is happening to the cloud of electrons as I remove electrons? And is that going to affect how strongly the remaining electrons are attracted to the nucleus, and therefore how much energy it takes to remove each one? In other words, if we remove more than one electron from the same atom, how do you think the energy needed will change from one electron to the next? All right, our next step is going to be to look at the technique of PhotoElectron Spectroscopy, which is how we measure ionization energies for elements.